So welcome again to Energy System Modeling course, lecture number 7. And today it's about energy transmission and distribution, well, more about this transmission. So I wanted to take kind of a broader view. I've seen a lot of these energy system modeling courses where they focus solely on the electricity system. So we're going to go through a bit of that, a bit of the district heating system, and something about the gas network as well. So it's a bit of a kind of like a sneak preview from these topics. So energy networks in Finland, electric network, and related to this electric network, we're going to go through this example related to linear programming optimal power flow. And then district heating network and the gas network. And I tried to kind of gather these analogies between these different transmission networks, what kind of equations and phenomena are affecting in these. So the energy networks in Finland, we have electricity, district heating, and natural gas pipelines, and they are constantly transferring significant amount of energy. And kind of key characteristics of these networks is that if you're talking about electric network, it's a lot easier to build compared to this gas network. The gas network operates at a high pressure, but the downside is for the electricity network is that the gas network actually has much higher capacity to transfer energy. At this point, I'm still going to check that I'm recording and that I have the correct microphone in here. Yeah. And if there's any troubles with the sound, just give me a heads up again from Zoom. And the recording seems to be on as well. Yeah. And then the district heating networks, what characterizes them is the higher thermal inertia, inertia in any sense. Gas network also has some inertia. You're talking about this line pack effect, which actually showed when they blew up this Nord Stream gas pipeline. So there was a huge amount of gas packed in the lines itself, and it was emitted to the atmosphere from there. Actually, at the moment, I think Nord Stream pipelines are not operational. So they managed to sever those connections, they being whoever it was. There has been a lot of speculations whether it was Russia or USA or that it was a CIA operation. I'm not aware what's the situation regarding the investigation related to that, but that was a successful sabotage. So for Finland, we have more than 400,000 miles of electricity network, 16,000, not miles, but kilometers rather, 16,000 kilometers of district heating network, and about 3,200 kilometers of natural gas pipelines. So that's an extensive energy network. And the one that's being planned and to some extent, I guess, also constructed is the hydrogen pipelines. So that's going to be the future network. There is some possibilities of blending hydrogen into this natural gas pipelines, and that's kind of like a research field of its own at the moment. So related to these, to the electricity network, there are 3 million electricity users and hundreds of power plants generating energy in Finland. And we have these power transmission links to neighboring countries. The transmission lines to Russia at the moment are not being used. They are still connected, but if you've seen the videos from what happened to Estonia just a few days or a few weeks back, they like physically disconnected from the Russian network. So we're part of the European power system and electricity market. So that's the Nord Pool that Finland is operating under. Quality and security of the electricity supply is constantly being improved, and I think in some Fingrid video I saw that it was the security of this electricity distribution to the customers was something like 99.99998%. So there's very small power outages anymore. So there still needs to be some development done, especially we talked about this, I guess, last time, or at some point also about the north-south connection being a bit too weak at the moment. So that's being taken care of, and Finland is only one price area. Most of Finland was electrified in the 60s, and in the 80s, the electricity grid pretty much covered the entire country. And there are still a lot of these old distribution networks. A couple of years back, near my house, there was the lines were dug underground, so that makes the distribution network really secure. So there's a lot of investment going on. So hundreds of millions of euros are poured into that. And by the way, it's not a good idea to sell these distribution network operations to anyone else, as they've been doing in Finland. So don't sell a monopoly. That's what happened. Pretty much happened in Finland. They started selling those networks. Not a good idea. District heating network. More than 200 district heating networks have been built in Finland. So cities, municipal centers, and larger urban centers. And they are extended each year by hundreds of kilometers. And around half of Finland, or half of Finnish people have this district heating. So, and the security is, again, pretty much 100% because it has this high thermal inertia. So if one of the power or the district heating power plants, or production plants rather, not power plant, but if some of those plants has an outage or maintenance, it doesn't affect to this energy security. Gas networks, natural gas network transport methane. So it's imported via LNG terminals and the Baltic Connector pipeline. So we have completely, well, not disconnected from this Russian gas pipeline, but we don't utilize the connection at the moment. In addition, there's biomethane that's being fed into the system. And transported through high-pressure transmission network and distributed to end users using this low-pressure distribution network. And for example, the place I live in, Lempäälä, between Kuliu and Sääksjärvi, there's this natural gas pipeline that, and I'm guessing the houses that were built in somewhere close to 2000 in that area, they were, I think it was somehow mandatory for them to take the natural gas heating for themselves. But 2 years or 3 years back, when the natural gas prices started soaring because of this energy crisis, they quickly started changing those systems. So a lot of them got, for example, this maalämpö, what's that in English? I'm having an outage. So the heat pumps that you take heat from the ground. And gas network has around 30,000 end users, most of which are small users. Well, this stove users, so meaning the houses that use this natural gas to heat. But that's very uncommon compared to, for example, Germany. And the majority of the gas is used in chemical industry and power plants. So regarding the electric network, when you're talking about this transmission and distribution, so we have the transmission network, and after that, you have the distribution network. So the purpose of this transmission network, it operates on a very high voltage level, which means that the energy losses are smaller. So the purpose of this transmission network is to move large amounts of electricity over long distances. Voltage levels, typically 110 kilovolts or 400 kilovolts or higher, to reduce energy losses. Requires high voltage power lines, substations, transformers, and I think it's a bit funny that I'm going to show you a map where you can see a lot of this stuff, and it's out in the open. So I think that's critical infrastructure, and to my opinion, it shouldn't be as widely distributed information as it is right now. Operators typically managed by these transmission system operators at a national or regional level in each country. And as you can see from the figure, there's usually large electricity producers that are being connected to the transmission network that cover pretty much the main load of the production. And in the distribution network, you can have these small producers also feeding the electricity to the network. So the distribution networks delivers electricity to end users, so voltage levels are much lower. So distribution substations, transformers, underground cables, and overhead lines are being utilized. And this is managed by this distribution system operators. So Fingrid is pretty much the one that's operating this transmission lines. Nordic synchronous area. So Finland is part of this Nordic synchronous area, and as you can see, there are other synchronous areas in Europe as well. For example, Ireland is its own island, and a lot of the Central Europe, or all of the Central Europe, it's one area, and then there's the Baltic area in between. So Sweden, Norway, Eastern Denmark is on the same area. So we are connected to Sweden with this AC connection, and also a smaller connection to Norway. And then there's high voltage direct current transmission lines. So the C cables, rather than using alternative current or alternating current, they use this high voltage direct current. And I'm not an electric engineer, so I would probably butcher the explanation, but the transmission losses are smaller in this way. So there's a certain environment which is under the sea, and also certain line length that has started to favor this direct current transmission lines. So I don't know if that's a fairly new phenomena that they are being built to this extent, but at least the undersea cables, for example, this Fennoskan and Fennoskan 2 are this direct current cables. I'm guessing there's this might be closer to 500. So from Rauma to Dannebo and Rauma to Finnböle in Sweden. So 2 cables. And by the way, as I mentioned before, the international sea areas don't extend to those cables. So if somebody is to cut those cables, they cannot say that it's, that was an accident. It's then rather deliberate. And there's also transmission link to Naantali, around 100 megawatts. And Nordic synchronous area connects to other systems via direct current connections. And Finland and Estonia, there's a transmission link in there. And I'm guessing at the moment the other one is still. Was it so that the other cable is still being under maintenance? I'm not sure about the situation about that. What else? So power system, power plants, main grid, high voltage distribution network, other distribution networks, and electricity consumers. So Fingrid is the responsible party for the functionality and maintenance of Finland's grid. And they have a lot of these neat videos where they do this maintenance work, which in Finland is a lot of cutting a lot of trees. So there's a lot of lines going through these heavy forest areas. So there's a lot of snowfall in the lines. So they have to make sure that those are those are being kept intact. So the main grid serves the producers and consumers both. So it's to enable them to trade internationally and nationally. And of course, the majority is consumed in Finland. The electricity is consumed via this main grid. So monitoring, operational planning, balance services, grid maintenance, construction and development, and so forth. So they are being the ones that plan the future. And for example, as I was talking about the kind of power disparity between the wind power production in the coastline, and then so there's a lot of production in the northern parts and the coastline, and the consumption is higher at the south. So Fingrid has to be aware of these developments, and they have taken actions to strengthen those connections. And then the distribution networks, they operate at a lower voltage. And from here you can see kind of like the backbone of this Finnish electricity system. And if you click in here, you're going to see a map of this electricity network. So you can examine the connections. I think this map has a rather poor legend, but let's bear with it. So you can zoom in on here and see, for example, I'm guessing this was the power line from Olkiluoto. So there's Eurajoki, Olkiluoto power plants, and this is a neat feature in this map. If you zoom in on it, it's going to change to satellite image. So it shows you pretty much all the connections everywhere. So you can see, for example, where the Olkiluoto 1 and 2 power plants and where the 3 starts from here. And this line that runs from here, let's follow it. So it runs straight to Jämsänkoski. So there's a factory and it runs right there. So you can see this as a really like detailed level. And it also shows you this how much this liitäntäkapasiteetti. I'm not sure if this is in finish in anywhere, but this liityntäkapasiteetti means that how much I assume that how much more capacity can be added in there. And you can see also, let's see if it has this legend. So these power plants area, mostly they are in here, they are related to these wind power plants. But for example, in here, I guess there's the Kalanti solar power farm. So that's the area that's being reserved for that. And so it shows you how much more tuotannon liityntäkapasiteetti, so how much can be added into here. So 480 megawatts. But on the coastline, you can see that there's a lot of these gray dots. So liityntäkapasiteetti 0 megawatts. I assume that it means that if they want to attach more power in their power production in there, they have to strengthen the capacity. So there are transmission limits, and since a lot of the wind power is being built in that area, they also need to strengthen the capacity to transfer it. So this is a really nice and I think a bit too detailed map for our own good. But I guess Fingrid knows what it's doing. So you can see the capacity, the power lines in here: 400 volts, 220 volts, 110 kilovolts, and there is, I guess it was somewhere around here. There was also one this 50 to 60 kilovolts. I'm not sure what that purpose of that line is. This was from 2018, but you can see a lot of these similar maps. This Metsälinja, I'm guessing here, is one of the main improvements. So you have more kind of transfer capacity between the northern and the southern part. So that's a new kind of 400 kilovolt line. And that's a bit small text, but hopefully you can see it. Available domestic capacity in 2023 or 2022 and 23, it was around 13,000 megawatts, and estimated peak consumption during 2007-22 was over 15,000 megawatts. So there's this domestic power balance, which has, by the way, been to some extent being filled because of the wind power. But since it's fluctuating, we're still going to have these kind of power gaps. But the import capacity from EU countries is 3,400 megawatts. So from Sweden comes the most, and Norway isn't even mentioned in here, but I'm guessing it was somewhere close to 100 megawatts. And there you can see EstLink 1 and EstLink 2, and this Fennoskan and Fennoskan 1 and 2. And they are this high voltage direct current. And in here you can see there was an article related to this. So the AC terminal cost, as I said, I'm not an electrical engineer, so I cannot explain to you fully why it is, but this DC terminal is a lot higher in terms of investment cost. But the losses, if you have a long transmission line, and especially if it's undersea, the losses are going to be significant in this AC line versus the DC line. So that's why they are favoring these high voltage direct current lines over the AC lines. So then about the kind of optimization of that network, I have added this linear programming optimal power flow problem in here. So this kind of a mathematical optimization is used to determine the optimal operation of a power system, with the goal of minimizing or maximizing certain objective, such as the cost, efficiency, or loss. So you want the energy security in a way that you don't overshoot the production in certain area, and then the transmission line capacity is being exceeded. So you have to have this energy security, but also you are aiming for this economic dispatch. So the economic dispatch means that you have the kind of lowest marginal cost for the system to operate. And in our models, in this SPINOP model, you're assuming that everything is ideal, so you don't have, for example, internal transmission these limits. But in here, we're going to see what it's going to do. So this is a really simple problem when you're solving it with this linear programming. So we are going to assume that the power is going to behave pretty much as in direct current version. And I have a video linked in here that you can watch that explains, well, they start from the alternating current equations, and then they kind of explain why you can drop out this and why you can drop out that, and why does it kind of converge to the fact that you can use this DC analogy in here. So the optimization problem is formulated as a linear programming problem, meaning that the objective function constraints are linear. And this refers to the optimal power flow refers to the process of finding these optimal settings for this power generation. And the objective, it can include minimizing generation costs, so this economic dispatch, minimizing transmission losses. So we're not exactly talking about the transmission losses in here, but we are talking about when you have this line reactance, which is kind of similar or analog to resistance in these DC lines. So AC lines, this reactance, we're taking that into account, and we're trying not to exceed these transmission capacities. So power balance, you have to meet the power, and you can see from this FinGrid pages that how well the power balance is being met based on the frequency measurement. And then you have generation limits, voltage limits for these buses or nodes. They use this term bus in this electrical engineering. So line flow limits transmission lines to prevent overloading. So let's see. We can use this superposition. So refers to the principle that effects of multiple independent influences of a system can be added together to determine the overall effect. So this superposition principle is directly applicable to this problem because of the objective function. So minimizing cost and this power plant limitations are linear. So basically what this allows us to do is to analyze the system as a sum of these individual components. And this is going to be our system. We have two of these production nodes and one consumption node in there. And all of these lines have the same reactance. So from 1 to 2, 2 to 3, 1 to 2, they are going to be the same reactance. So, and all of the lines are equally long. So flow from, let's see, point A to B. So flow A, yeah. Sorry, I don't have the flows in there, I guess. But basically from this A, if you are going to flow, have the electricity flow, it's going to be length of 1, and from A to B to here, it's going to be 2 times the length. And we have flow limits in here. So the flow maximum limit from A to B in here is going to be 200, or rather 1 to 2 is going to be 200, and 1 to 3, 260, and 2 to 3 it's going to be 200 megawatts. And the production capacities of these systems, power plant A or the generator A is going to be 390 with this marginal cost of 10 euros per megawatt hour, and C is going to, or rather this B is going to be 150 megawatts maximum, and there's going to be 20 euros per megawatt hour. So if we are trying to get 450 megawatts out of there, the economic dispatch solution is going to be, that's going to max out the cheaper plant, and then we're going to take the rest from the more expensive plant. So that's the economic dispatch solution. But since we have these transmission lines, or rather transmission line limits in here, we can apply the superposition in here and see if this one is exceeded. So this one doesn't mean if we're inserting 390 megawatts from here, it's going to flow from 1 to 2 and to 3, and also from 1 to 3. So it doesn't necessarily mean that 390 megawatts is being transferred in between there. So linear additivity, a hard word. So there's going to be this flow A and flow B, and it has to result in 390 megawatts. So that was the limit for this generator A. So since we have twice as long cable from 1 to 3 versus 1 to 3, and we have the same reactance, so it's pretty much analog to this resistance in DC systems. Then what it means that our flow from 1 to 2, so this flow A is going to be 260 megawatts, and this is going to be twice smaller. So does that make sense? Yeah, more or less. And then if you have 60 megawatts in here of the power, you have, again, from 2, 1, 3 line, you have twice the length, so twice the reactance, and 2 to 3, that's going to be twice as large in terms of power flow. So 40 megawatts from FC and 20 megawatts from this flow D. So let's apply the superposition. So we're going to add both of these productions, 60 megawatts, 390 megawatts. So we're adding FA, FB plus FD and FC. Oh, my animations are failing in here, sorry. So here you have 130 megawatts flowing from 1 to 2, and then you have 20 megawatts flowing from 2 to 1. What's that going to equal? It's going to equal 110 megawatts. And again, if you have 40 megawatts in here, 130 megawatts in there, between 2 and 3, you're going to add them together, you're going to get 170 megawatts. And from here, between 1 and 3, it's going to be 260 and 20. So we have 280 megawatts. And it results in 390 megawatts, but we are exceeding the line transmission limit. So something has to be done. The economic dispatch model doesn't yield a satisfactory result since we are exceeding the transmission limits in here. So the flow between 1 and 3 must be reduced by 20 megawatts. And if you were to reduce or cut out the 60, then we would meet the demand of reducing this by 20. so to 260, but then we wouldn't get 450 megawatts. And I'm guessing I'm having a miss or an error in here. Let's correct that right away. So that's slide 16. I should have 450 megawatts in there. So let's see. 16 and here should be 450. Yeah. So let's get back to business. So another solution is that we reduce the generator A input and increase the generator B input. And now, if we have 330 megawatts, then you can also divide it based on this reactance and the flow lengths, and you get 110, 220. And if you have 120 megawatts in here, then it's going to be 80 and 40. And if you apply the superposition principle and calculate those together, you're going to get 260 megawatts into here. So what that means is that this optimal power flow solution is more expensive than the economic dispatch. So basically what it means is that if you don't have the transfer limits or the transfer capacity, then you are unable to utilize the economic dispatch. And this has been happening. For example, Germany has been having rather weak link between the north and the south, and there has been a lot of from time to time there has been a lot of electricity from renewables in the northern part, and they have been unable to transfer it back to the south. And if the situation in Denmark, Norway has been in a way that they are not having power shortage, then curtailment is the only possibility. So this is pretty much all fun and games if you have dispatchable systems. But if you have renewable production, then this starts to make your life a bit more difficult. So this is the basic principle that you can utilize in these calculations. Of course, this is pretty much the most simple solution that, or the most simple example that you can find that's kind of like complex enough for us to get anything out of it. And this is gone through in this YouTube page. And as I said, in this video, they go through it from the beginning, from the power flow, from the AC power flow equations. So you have the phase angles and all of these terms are kind of explained how you converge to this simpler form of utilizing this DC analog in here. But since I'm not an electrical engineer and this course is not solely on electrical networks, I'm going to leave it out of the scope. And if you want, you can see the video with a better explanation than I would ever make. But linear program optimal power flow problem. And what that also means that we have to pay for the kind of energy security. So contingency in power systems refers to unexpected event such as failure. So if there's going to be some failure of this line, so you cannot transfer any electricity through here. So what it means that this system would most likely, it would be overloaded and the whole system would trip. So you have to plan ahead for these incidents. So unacceptable because this overload of line 1 and 3 leads to cascade trip and system collapse. And this kind of a overall system collapse, I didn't see when was the whole Finnish electricity system, when did it trip, or when was the kind of largest major tripping before, but it hasn't happened in, decades. I'm guessing it's almost 100 years. So in Finland, there has been a real nice management of this electricity system. So then about this district heating network. So in essence, this is going to show for you in those, for example, spin-opt calculations that between the nodes, you're just going to set transfer limits. So you cannot transfer more than this, and the model is going to take that into account. But that limitation arises from these physical power lines, that if they don't have enough capacity, then that's the kind of reason in the real world. There's also ChatGPT's nice illustration of a district heating network modeling. So again, we can talk about transmission and distribution. So in this power lines, I'm guessing it's a bit easier to understand and make this division. And I'm guessing this division in some sense could be made another way in district heating networks as well. But the transmission, you could say that it's the primary network. Transports heat from power plants, waste heat sources, large heat production units over long distances. And long distance doesn't mean as long as in the electric system. So the electric system, that's much more, or rather this one is much more localized. So heat has always had the problem that it has to be produced and consumed on site because of the losses. So the electricity network, it can have losses up maybe a couple of percentages if you transfer with high power transmission lines from north to south of Finland. But in district heating networks, for example, in Tampere, it's just shy of 10%, maybe 8 to 9% the overall loss during 1 year. And you could, of course, start to decrease that loss by insulating the pipes more, but then it would cost a whole lot more. So what's the, and operates at higher temperatures, and the initial district heating networks, it originated, I'm guessing, from the United States or Canada. I'm not sure which one, but they were using steam in there. So it was close to 200 degrees. So it was really inefficient also. But typically nowadays, we are aiming for lower temperatures. And at the moment, as I've been mentioning about this, my PhD workers, Juhani Kotilainen's thesis work, it's about trying to find, well, the first article was trying to find whether it's feasible to decrease the supply temperature of this transmission network. So that would mean that it would be, for example, 90 rather than 115, the maximum supply temperature. So what it means is that you have less heat losses, but then you have more pumping. And the main problem, of course, is does the customer have in the secondary distribution network? So kind of like the connection point between so that's pretty much the transformer. You have the heat transfer unit. Does the heat transfer unit have the capacity for operating under lower this transmission network supply temperature? So transmission is the primary network, and the secondary network is the one that's running around in here. So this one. And that's connected to this main grid, so to say, via the heat transfer units. So all of these houses in the basement usually have some kind of a heat transfer station where the primary network and the secondary network connect. but the same water doesn't run through them. And in here, you can see the supply temperature as a function of ambient temperature. So usually there's this kind of a heating curve. So what it means that the colder it is outside, the higher the supply temperature is going to be. So you have more power that you can transfer. And then you have the customers in between in here. So there's the supply line on the red and the return line on the blue. And you have to have a certain amount of pressure difference that's been managed by these pressure valves. And then you have these pumping stations. So you have to increase the fluid power, or the fluid pressure rather, for it to flow. So the flow always goes from higher pressure to lower pressure. So we have higher pressure here, and you have to have high enough pressure for the fluid to flow. And what's restricting the flow is the friction. So the more you pump, more friction. So the more you pump, more it costs. And the less you have supply temperature, and these houses are still having the same demand, if they are having the same demand, and you have smaller supply temperature, then you're going to have to pump more water. It's going to cost more, but you're going to have less losses. And based on Juhani's preliminary results, it seems that this kind of a system that hasn't originally been built for operating under lower temperature levels, it's unfeasible to start decreasing the supply temperature. The savings are so minimal, and it might cause problems in the customer end, that it seems that if it's not being built for that, then there's going to be a problem. But as I said, preliminary results. The article is at the moment being is submitted to a scientific journal, so we'll see if it goes through peer review. And this test is thermal energy storage. So that increases the thermal inertia of the system. And this is an example of the district heating network. So it's kind of has an analogy to this electrical network as well. So something is being produced, something is flowing, you have customers at the end, there's transmission, there's distribution. But in here, there's no kind of a voltage to drive. So this is the pressure difference that's driving the flow in there, and not the voltage difference. And in here, it's in Finnish, but this means kaukolämpöverkon pituus means that the length of the network. There's some 50 kilometers and some additional lines as well. So maybe 60 or 70 kilometers in between there. And the volume. So this is over 200 cubic meters. What kind of power plants in this current or this specific networks? 4 megawatts, 90, 5.5. Actually, this is consumption in here. Yeah. And bioheating system, 20 megawatts. So basically, transmission network shown in here. These were also on display on the internet to some extent. But I'm guessing, at least, I'm not sure if it's the fact, but at least I've been having a harder time than before finding these. So maybe due to the war, they have been actually been a bit scared and trying to hide this critical infrastructure. So I'm really amazed about this FinGrid page that, hey, please check out everything. And you can see the satellite images of everything in there. So in a district heating network, the supply and return temperatures are dynamically adjusted based on the outside temperature. So heat demand, energy efficiency, and heat loss minimization all affect to that. So 120 when it's minus 15. So this morning, your power or the district heating plants would have produced in their heat transfer units water for the circulation that would have been 120 Celsius. And it might lower 1 or 2 degrees when it moves from the plant to the consumers. So buildings require more heating when it's cold and less when it's warm. And to maintain this indoor comfort, networks increase the supply temperature in cold weather. And the regulation is done based on this heating curve. And I draw also this return curve in here. And in the return curve, we were discussing about this with Juhani yesterday, why it is why it is so that during the summertime, for example, you have this higher return temperature, but that is related to the substation. So the substation is the one within the house. So that's called the substation. So the substation kind of temperature requirements, and also there's the fact that how much hot water heating is being emphasized. So during the summertime, it's much more, the curve is much more emphasized or dictated by hot water consumption rather than just the household heating. So that affects to this curve. And in here, you can see it in action. So this is district heating network as a function of time. So this is summer, and this is winter. And in the winter, the supply temperature, the colors, of course, should be vice versa. So this is the hot side. And in the winter time, it's higher. In the summertime, it's cooler. And for the return temperature is vice versa. So in the summertime, the return temperature, as there is less heat demand in there. Even though you lower this temperature, there's less heat demand, so you don't extract as much power as during the winter time. So what's the power amount being consumed by all the consumers is the mass flow in the network and the temperature difference. So based on the temperature difference, you can calculate the enthalpy difference. So mass flow times enthalpy difference. And this is what Juhani was kind of calculating. So the figure in here illustrates really kind of a simple system. So profile of a district heating network when the supply water temperature is being lowered. So this one is the figure that's it's referring to. And this system has 2 pumping stations. It has a heat distribution center, so this kind of a substation, and the return line. So what happens in the supply line? The temperature is high and the pressure is high in here. The pressure starts lowering because of friction. Then you have a pump, it spikes up and then lowers. Then you have a pump again, spikes up, pressure decreases, and then usually in the return lines, you don't require those pumping stations. In some cases, if you have a lot of elevation, you can use those. But the lower temperature, what that would mean is why you have a higher pressure in here, because you have higher flow. Since you would have less delta T, so less delta H. If you still want to extract the same power, it means that you have to have more mass flow. And if you have more mass flow, you have more friction. If you have more friction, you have to overcome it by the pumps. So lower temperature would mean that you would overshoot the maximum pressure. So that means that the pipes could rupture. And then in the return line, if it goes below the minimum pressure, then it would start boiling. So it has to have enough pressure in the pipeline or the system or the water rather not to start boiling. So if you have 120 or 120, well, that's not actually the case in the lower pressure. now I was talking gibberish. It's not going to start boiling in there. It would start maybe boiling on the upper end if you reduce the pressure enough. But in here, the minimum pressure is more related to the flow direction. So it wouldn't have enough pressure to get back to this power plant. So network is simplified and includes this production plant and this consumption in here. And as I was explaining, this lowering the supply temperature. So this would provide less temperature to the flow, means more friction. Yeah. So the main equation related to this district heating network modeling, you have the mass conservation. So it's pretty much the Kirchhoff's law. So energy or mass doesn't kind of disappear. So you can make this in the Kirchhoff's law case, you could use current and make for each node that you have this balance of these currents. Yeah.
The temperature will remain constant or what? Pumping pressure?
In here. Oh, yeah. The temperature in this case, if you were to, that's a good question. So does the temperature remain constant in this system? So how would the temperature react in here? If you had an idealized system in case, in terms of having infinite amount of insulation, that doesn't affect to the friction. The friction still remains. So you could say that the temperature from this plant till this distribution center would remain constant, and then it would drop to a certain level and then again remain constant. Yeah, the consumption, yeah, this distribution center. So the substation decreases the temperature, so it draws out the power. So you go in this temperature, and then you jump out in this temperature. So that is what's happening in the substation. There is so there's a heat, there's kind of a heat transfer in a sense that this battery or the radiator flow goes into the substation and draws some power in form of temperature rise. So I'm going to draw it. It's easier like that. Sorry?
The line, there will be any temperature drop in the line itself.
Yeah, if you had an kind of infinite amount of insulation, it's going to drop just a bit, but even though the friction is taken into account, if you have an idealized system like that, what the temperature would be, that the temperature would remain constant, then it would drop in the substation, and if I draw the return line backwards like this, it would remain constant. So this would be temperature, and this would be distance, and there would be the substation. And what would happen in the substation when it goes into the substation? So this is the inlet in here. The temperature, the hot temperature starts, the temperature starts decreasing. So there's T, and how much power is drawn is based on UA delta Tm. So logarithmic mean temperature difference, and this is the water that's coming from the radiator. It comes to the substations to heat up. So it draws power from here to here since there's the temperature difference. So in here, the temperature would remain rather constant, then it would drop, and then again remain rather constant. But as in electrical network or electric network, since there are losses, the same thing applies to here. So mass conservation. Mass doesn't disappear, energy doesn't disappear. So you can say mass and energy is conservation for all of these points. Then there's momentum conservation. So you can use that to calculate the pressure drop. Energy conservation also for this heat transfer system. Then there's time delay and dynamic demand and supply balancing. And that's something that we kind of did in the previous exercises where we had this demand curve for district heating network. And then we were saying that how much you're going to utilize different power plant, or rather production plants. I'm talking about power plants in here. We're not producing power, rather we're producing heat, even though if it were a CHP plant. Mass conservation continuity equation, you can use that. So for a steady state incompressible flow in a pipeline, mass flow equals density, cross-sectional area, and velocity. So that's something that you all have to know. You have to be able to apply that, because that enables you to calculate the velocity of a system. You have, for example, DN400 pipeline. It's 40 centimeters or 0.4 meters in diameter. You have a certain flow, and the density can usually be said that it's close to 1,000. And you can use, for example, X-team to calculate it. So based on that, you get the velocity. And for multiple branches and junctions, you can make this M in equals M out. So momentum conservation. So this is the Darcy-Weisbach equation, and that's derived from the Bernoulli equation. So Darcy-Weisbach enables you to calculate the pressure drop, pressure loss. And this is going to be the same for the gas transmission network. So in here, you just need to calculate the Darcy-Weisbach friction factor. And in the exercises, we're going to go through this by using the Colebrook equation. The Colebrook equation is somewhat tricky. I guess I have the equation in here. So this is the Colebrook equation for friction factor. And it's rather peculiar in a sense that you have F in here and you have F in here. So when you start to solve it, it's usually solved through iteration. And what you need for it is this coarseness of the pipe. So if you have a really coarse pipe, it causes more friction. If you have a smooth pipe, then less friction. For energy engineering students, I hope this is rather familiar if you've gone through the thermodynamic courses in which you calculate the pumping power. So that's kind of like a trick you have to know if you're dealing with these piping networks. Darcy-Weisbach and Colebrook equation. There are simplifications for this Colebrook equation, so you don't always have to use the iterative form for it. Then energy conservation. So you have heat transfer by convection within the fluid and conduction through the pipe walls. So you have heat loss to surroundings, overall heat transfer coefficient, heat transfer surface area, and the logarithmic mean temperature difference. So this is what causes the losses. If you have cold ground, then you have some heat loss from the hot fluid to the ground. And that's basically how you can calculate it. So you need the heat transfer calculations, especially for determining this U. So that means the overall heat transfer coefficient, it has the convective heat transfer from the fluid to the pipe surface, through conduction through the pipe, and then conduction to the external ground. Then there's the time delay, so the transport delay in the pipelines. If you're going to crank up your production plant in Hervanta, and you are expecting it to have an effect on Tampere city or the downtown, then it's going to take some time. And of course, there's the flow direction. So if flow is going the opposite direction, it's not going to affect it. So that's why you need this thermohydraulic modeling tools. So for example, this fluided heat. So you have the map topology in there. You're going to take into account all the crisscrossings, all the nodes in here represent, for example, consumers, and you can, in fluided heat, you can inspect a certain portion of the line and so forth. So in these calculations, what we are doing in Excel and maybe with Python, they're going to be oversimplified, since it would take an excessive amount of time to start calculating this kind of a network by hand or by your own code. So that's where we're going to stop. You're going to learn what's the kind of basic underlying idea behind those calculations. And then when you do it, you have the ability to kind of deduce what's going on inside the black box. So this time delay would be taken into account with these design programs. For example, in here, we didn't have any time delay. So that was from, I'm guessing, lecture number 4. So when we were talking about the production or consumption, I don't recall. But still, we were doing this in the exercises. So this was the optimal dispatch order of certain systems in the district heating, or the certain production assets in the district heating network. So this doesn't take into account anything related to the time delay. It's all energy in and energy out, and everything is like, it's like analog to Biot number in heat transfer. If you have a really small Biot number, it means that the system is thermally thin. So it means that everything you put inside in here, everything is immediately distributed to everywhere. So that's not the case, and that's why you would have to take into account this time delay. And one thing I want to kind of also take into account in the exercises, because that's also something that Juhani is calculating, is, for example, if you have let's say a data center that produces heat that it's significantly lower temperature than the one that's coming from the production plants. It would be nice to use it because it has a lot of energy. But if it doesn't have the exergy, it has the temperature, then how much you can kind of dilute the water that's coming from the power or the production plant with the water that's coming from the data center. And do you have to kind of crank up the main plant for the data center to be able to fit into the system? But related to this pumping calculations, what we are going to be going through in the exercises is, if you have a certain, actually what I did in here is I utilized the same data that we used in the district heating network system. So this is a familiar figure for you, I guess. So it has the outside temperature, and it has the production, or rather the consumption of the customers. Now what I did in here, I scaled it up between 0 and 10 megawatts. So I wanted the scaling to be done in a way that my system would have 10 megawatt consumers. So in essence, we have a similar system as in here. Now I would just have only one pump in here. So production plant, pump, and this substation related to this heat consumption. And the maximum heat consumption would be 10 megawatts. So based on this heat demand curve, or this heating curve rather, these are rather arbitrary numbers, but this is the way it's being kind of determined. So if you have found optimal heating curve for your system, If it's below 20, then it's going to be, or 15 maybe in here. No, 20. If it's below 20, it's going to be flatlined. So you don't produce any higher heat. And then it's going to start following this linear function, and then again you flatline it. So if you have a supply temperature, or rather the outside temperature here, that's going to determine your supply temperature and return temperature based on those heating curves. And what is going to determine your customer demand is this one. So if you have a customer demand of 11 megawatts, the DH for water, so basically how much enthalpy are you going to draw, how much energy are you going to be drawing from the water or power, is based on the temperatures. So it goes in hot, comes out cold. Yes, now works. Then you have the DH of water, and for the mass flow, you can calculate the mass flow based on DH and customer power. And again, from the continuity equation, you get the velocity. Based on thermal properties, you can calculate the Reynolds and system diameter, or the pipe diameter. You calculate the Colebrook, and then from there we get the pumping power. And actually, if you plot, let's try and plot the pumping power as a function of this outside temperature. Bear with me a second. So I'm going to move this one into here. So you're going to see it's a rather peculiar behavior. But what it tells us that the higher the temperature, the less pumping power we're going to need in our system. And if you start changing these values in this Tmax, so let's put Tmax to 120. So it changes the system. So that's what we are going to be looking at tomorrow and on Friday. A little bit something about the gas network. So the gas network, in essence, it's rather similar to this district heating system, but it's not dealing this. So it has a flowing flow inside it. So that's the kind of similarity to this district heating system. It's not transferring heat, it's rather transferring chemical energy. So in that sense, it can provide a lot more power. So it's the same as you're kind of charging an electrical vehicle versus you're putting in gasoline. Your gasoline pumps energy transfer, so the power, it's going to be 100 to 1,000 times higher. So it's going to be in the range of megawatts if you start pressing the handle from the gas pump. And if you put electric vehicle to charging, it's going to be maybe tens of kilowatts mostly. So there's a huge disparity. And the same goes for gas network versus this electrical network. So you can transfer a whole lot more power in here, but of course it's a bit more tricky to build. And the driving force in here, again, is the pressure. So that's the same thing as in the district heating network. If you have a flow, the driving force is going to be a pressure. If you have electricity flow, it's going to be the voltage difference. So you have to have a higher pressure in the refinery end. So that's why you have to have these compression stations. So in the refinery, you would have a compressor that would pump up the gas pressure, and then it would start flowing through the pipeline. And the pipeline resisting factor is going to be the friction. So the smoother the pipe, the less the friction. So huge, this transmission network, it can go, well, between 30 and 100 bars. Use large pipelines and compressor stations managed by gas transmission system operators. And in Europe, it's typically a cross-border network. So coming from Russia, for example, through to the Central Europe. Gas and oil production or some other injection to the pipeline at this end goes to refinery. You clean up the gas, for example, decrease the sulfur compounds from there, or clean up the sulfur compounds, and this is pretty much sulfur-free. So then the refined gas flows through the pipelines. You have compression stations, and then you have gas consumers, power plants, and domestic and commercial. And that's the distribution network. So that would be a lower pressure gas grid. And that's the same that's flowing right close to my home in Lempäälä. So the low pressure distribution network. So all of these systems, they have this transmission network and they have the distribution network managed by gas distribution system operators. Gas network in Finland. There was over 3,000 kilometers rather of this network, and includes 2 points that cross state borders. Imatra border, and this Imatra border is not used anymore. And then we have the Baltic connector. Baltic connector is nowhere near, for example, compared to the for its capacity, it's nowhere near compared to these Nord Stream gas pipelines, but it's still a really important lifeline for us, has been after this Russia-Ukraine war. So it started, I guess, in the 2020, 1st of January. During 2022, 2 LNG terminals, so liquefied natural gas, were connected to transfer platform with new connecting pipelines, Hamina and Inkoo LNG terminals. So instead of being reliant on Russian natural gas, now we can utilize LNG and this Baltic connector line. Biogas is fed also into this Finnish biogas plants, but that's a really small amount that's being utilized. And the main consumption is in the chemical industry and in the power plants, but also households utilize this still. And May 22, 2022, when this Imatra connection was closed. So I'm guessing at the moment it's zero. So for example, so this was, for example, one project that was, or kind of energy line that was being, well, not severed, but disconnected at least. So the electricity doesn't flow between Russia and Finland. And this gas network is closed, and also this new nuclear power plant that was going to be built by, or Rosatom was supposed to be involved in it, so that was ditched from Hanhikivi. So the Baltic connector, 77 kilometers of bidirectional offshore pipeline between Inkoo. I'm guessing that's it in English. In Finland and Estonia, Paldiski. So 21 kilometers of onshore pipeline. So Finland is managing the pipeline on its own side when it's on the offshore, onshore, so on land. And also Estonia, the same thing, but this is kind of managed together. And I'm not really sure about that, but I'm guessing 80 gigawatt hours of gas daily can be transferred. That's a number that I saw. And as you can see, this Baltic connector manages us to kind of connect to these European gas lines. So Europe is pretty much filled with these natural gas pipelines. So Russia has been really important to Central Europe in providing this natural gas. So that was a bit of a bummer for all of those involved in using natural gas. And there's a lot of this, for example, these combined power plants, the thermal power plants that are being utilized all over Europe. I guess Italy has some, there was some 3,200 megawatt power plant complex, combined cycle complex that was operated in there. So there are huge power plants related to that. I didn't put the equations here because I'm not sure if we have time to go through them in the exercises. The main thing I want you to remember from these equations is this Darcy-Weisbach from the Bernoulli equation. But there are this Weymouth and Panhandle equations, and they are being commonly utilized in these natural gas and also hydrogen networks. So what that allows you to do is to calculate the flow based on pressure difference. It's the same as in the Darcy-Weisbach, but this doesn't require as kind of exact information. For example, the friction factor is a bit more loose determination in these ones. I put a book link in here. So let's hope it's gonna open it. Yeah, so from here you can see the Weymouth equation. There is still stuff to be inserted in there. And there's the Panhandle equation. So these have been commonly utilized with these natural gas pipelines. So the Weymouth assumes that the gas flow is highly turbulent, very rough, applies best to short pipelines. Turbulence has to be fully developed, and flow resistance is dominated by pipe roughness rather than viscosity. So high pressure transmission lines, gathering systems in short distance pipe networks. And well, there's the analogy that Weymouth is like flow like water rushing through rough, rocky riverbed, so turbulence dominated. And resistance comes from mainly the surface roughness. And then there's the Panhandle. So this is for long distance pipelines. And the analogy in here given is if the Weymouth is like a river, then this Panhandle is well-maintained road. Well, there's a car that still experiences resistance, but you're going to calculate it over much longer distances. And so this is something that you kind of have to be aware of, that there's a simplification with this Weymouth and Panhandle for this Bernoulli-derived Darcy-Weisbach equation. And line back is something that you also have to be aware. So pipeline volume, pipeline pressure, and gas properties, such as the compressibility, specific gravity, which is different, so compared to air, the density. So it's going to be different with hydrogen and natural gas. So how much, for example, hydrogen and natural gas have very different properties. So how much can you like dilute it? Well, that doesn't directly relate to line back. Line back is how much gas you have in the pipeline itself. So if you have 80 bars on this end and 40 bars on this end, well, that would be a huge pressure drop. So it would have to be a long line, but let's say 80 and 40. So the pressure levels are like this. What's going to happen if you close this end, so the production, and if you close the consumption, then the pressure differences are going to start to level out. And when they have leveled out, you have certain average pressure. And based on that average pressure, you can calculate the line pack, so how much gas is in there. But even though you're dynamically operating the system, so the pressure is going to have a profile in there, there still is gas in there. So it's not that simple to calculate as kind of said in here, but the basic idea is that you can use this as a buffer. So the higher the volume in the pipeline, the more buffer you're going to have. Line pack. So the analogies between these different networks. So the flow conservation. So Kirchhoff's law and mass conservation ensures that the Kirchhoff's law ensures the sum of currents entering and leaving a node is zero. And the same for district heating and gas systems. Mass flow in equals mass flow out. Of course, there's the compressibility factor. So with compressible flows, you have to take that also into account. Potential differences drive flow. So electricity voltage difference drives the electric current. Temperature difference drive heat flow, and also the pressure difference in this district heating system makes the flow in the system, but the power flow is based on the temperature difference. So in the gas systems, as in the district heating system, the pressure difference drive the gas flow. But also the power flow is related directly proportional to the heating value of the gas that's being utilized. So hydrogen versus natural gas. Hydrogen actually has much less density. So for the same volume flow, you have less energy with hydrogen, even though with the same mass flow you would have more. Transmission line equations, or the network equations. Power flow is modeled using Ohm's and Kirchhoff's law, AC/DC power. In the district heating, the flow depends on the mass flow rate and specific heat capacity, governed by energy balance equations. And in the gas network, the pressure drop along pipeline follows nonlinear flow equations, Darcy-Weisbach equation. Storage effects, so inertia and delay. No significant storage in transmission lines. Well, capacitance, inductance effects. But if you're talking about this energy storage, electricity network in itself doesn't have the capability or the capacity to store energy. District heating, there's a lot of thermal inertia. So that is by far, it's kind of like a thermal battery. If you have 600 kilometers of network and you have average DN30 or DN40 or 300 or 400, it means that you have a lot of water within the system that you can heat up and utilize the thermal inertia. In the gas systems, the line pack is the kind of analog to this district heating thermal inertia. Control mechanisms. In electricity systems, there's voltage regulation, frequency control. So the more voltage, so this voltage levels that you saw in there, it's the maximum one. And if you want to increase the flow, then you crank up the voltage difference. District heating, flow rate adjustments via pump, valve control, and supply temperature regulation. So flow is determined based on the pressure difference, but the energy flow is also being affected by the supply temperature. And in the gas system, compressor stations. Optimization and economic dispatch. In electricity system, minimizes generator cost subject to network constraints, as we saw. Optimal heat dispatch balances heat source efficiency, costs, and distribution losses. And you have to be aware that there's delays, time delays. If you crank it up now in this plant, it's not going to reach the other side of the network, but in a matter of hours. And gas flow optimization minimizes transport cost, compressor energy, and you have to meet the demand constraints. So you have to provide the customer with the assigned pressure for them. Perfect timing. Yeah. So tomorrow we'll see what we have time for other than the district heating network. Most likely I'm going to put some gas network calculations in there as well. And yeah, I'm going to also give you to Moodle this kind of a energy, the project work required data sheet. So you're going to start collecting the data. And we're going to see that after the exam week as well. So everybody who is coming to do the project work has to have all of this data ready at hand and download it. And next week is the exam week. Remember to advance the Moodle assignments. I'm going to put the third one most likely during the beginning of the exam week. And then we have one lecture before the visiting lecturer. So after exam week, there's one more lecture with me, and then 3 lectures with the visiting lecturer. Okay, I guess we are done for today. So see you on the calculation exercises.